Assalamu alaikum everyone. Today we have to start this new section which is about the separator part, and we know that when we are designing any process, then right after the reactor we have to study the separator part, because in the reactor we can get the products out of the feedstocks, and we can also get some byproducts, and some of the raw materials they are not converted into the product. So we have to tackle these three things into the separation section, and we have to use some kind of distillation columns or the flash separators, and we will see some of the details that how we can use the separators right after the reactors, and how many different types of separators we can use. So after the reactor section, the separator section should be studied. What happens into the separator section? So the feed is going into the separator. It can be a flash drum or it can be a distillation column, and from here we can get the product that we actually need. Sometimes we can also get some kind of byproduct, and sometimes it can be a valuable byproduct, or sometimes it can be an unrequired byproduct, and sometimes we can have some kind of waste which is not acceptable, and we have to just treat it and then send it to the environment, and we have to just make some additional treatments to this waste streams. Then, what are the important questions that we should have in our mind when we are planning or when we are designing the separator? Now, the first question here: what type of units should we use? Okay, so what kind of different separators we can have? Either it can be a flash separation, or we can have some kind of distillation column. Now, in these two types of separation techniques, we can have the horizontal columns, we can have the vertical columns, we can have divided wall columns. So there are a lot of categories in the separation itself that we need to consider, and every technique it has some advantages and disadvantages. So we have to study those processes in detail before finalizing the type of equipment or the unit we are going to employ for our process. Second question: how should the units be sequenced? So we will see that how many units that we have to use for the separation, and what should be the utility in that kind of separation technique that we're going to use, and if we are dealing with some kind of easier drops, and how we can handle that issue. So we will study this part in detail in the today's lecture also. What are the product specification for all the products? So it depends on the market demand, that what kind of product you need and what is the level of purification you require, because you know that if you are increasing the purification above the requirement, then you can decrease the profitability of the process, and you can reduce the profit margin. So we have to match the customer specifications, and we have to generate the profit at the same time. So we have to consider this thing also. Now the fourth question: are any of the products heat sensitive? So we have to take care about the products if they are heat sensitive, and either they can polymerize or deteriorate when we are supplying the heat, and then how we can actually control those kinds of products without reaching that heat sensitive points. Okay. Now here are some of the guidelines that we have to see while designing the separation units. So the first one: use distillation as a first choice for separation of fluids when purity of both products is required. So the first thing that we have to use here, most commonly, that we can use the distillation processes, and we can use these processes to increase the purity of the products. Okay. We can also use some kind of gas absorption to remove one trace component from the gas stream. So if you want to remove one component from the gas stream, then we can use the gas absorption process. Consider adsorption to remove trace impurities from the gas or the liquid stream. So in the adsorption, might have studied some kinds of adsorbents that can selectively remove the impurities from the liquids and the gases. Consider pressure swing adsorption to purify gas streams, especially when one of the components has a cryogenic boiling point. So you can also use pressure swing adsorption processes, in which we can use some kinds of adsorbents that attract the molecules of the gases or the liquids when the pressure is increased, and then when we release the pressure, those components will be released back. So this kind of process is called as a pressure swing absorption, and we can also use this process for the purification processes. Consider membranes to separate gases of cryogenic boiling point and relatively low flow rate. So we can use some kind of membranes that can allow certain molecules to pass through that membrane, and certain molecules they can be separated together. So we can use the membranes for the separation of gases if they have the boiling point in the cryogenic conditions. Choose an alternative to distillation if the boiling points are close or if the heats of vaporization are very high. Now we know that for the boiling points, for the constant boiling points liquid, we can call those mixtures to be the azeotrope. So if we are dealing with some kind of azeotrope, then we are limited with the distillation process, and we can reach a certain point, and after that point we have to use another technique. Okay, so you have to be careful while choosing the components that you are separating, that either they are azeotropes or they are simple liquids that have the large boiling point. So if the larger boiling points are present between the liquids, then obviously you can go for the distillation. Consider extraction as a choice to purify a liquid from another liquid. So liquid-liquid separation, we can use the idea for the extraction. Similarly, use crystallization to separate two solids or purify a solid from the liquid solution. So if you want to purify two solids or purify liquid from solid from the liquid solution, we can use the crystallization technique. Use evaporation to concentrate a solution of solid in a liquid. So if you want to concentrate any solution, you can use evaporation technique. Use centrifugation to concentrate a solid from the slurry. Okay, so if you want to separate a solid from the slurry, you can use the centrifugation technique. I will not go into detail of each of these process because it is quite general and you might have studied in the physical chemistry already. Use filtration to remove a solid in almost dry form from the slurry. So filtration technique, it is you know that to separate the solid from the slurries. Use screening to separate solids of different particle size. So if we are dealing with some kind of solids having different particle size, then we can use some kinds of screens having different mesh numbers to separate the solids on the basis of their particle size. Use flotation or the sink techniques to separate solids of different density from a mixture of pure particles. So these are the two techniques, flotation techniques and the sinking techniques, in which you can separate the solids on the basis of their densities. Consider reverse osmosis to purify a liquid from a solution of the dissolved solid. So the good example of this one is to get the water from the sea. So you can actually get the pure water through the reverse osmosis process from the seawater. Use leaching to remove solid from the solid mixture. So leaching is another technique which can be used to separate the solid from the solid mixture. Consider chromatography for final purification of high value products such as proteins, such as dilute streams. So this is kind of new technology which is mostly employed in the research. And basically in this technology, what we do, that there are two phases. One is the mobile phase and the other one is the stationary phase. And then we allow the constituents of having different mixture to move in some tube, and on the basis of their speed within that tube, there is a separation in that particular tube. So it can give you some peaks that can be later evaluated and differentiated on the basis of their molecular weights or the speed of those particular component in that particular tube. Okay, so this is also one kind of the separation technique, and also it can be used to get some kind of evaluation on the type of materials that you can have in one mixture. Now, guidelines for the sequencing separation unit. So when you're having more than one units in one process, then how we can arrange those units and which material should be removed first and which component can be removed later. So there are some of the heuristics that can be followed in this process. Remove the largest product string first. This makes all the subsequent separation units smaller. So if you are having the larger product in the product stream, then it is better that you separate that product first, and then you can have the smaller units later on. Okay, so if you are having more product separation at the first stage, then you can for example, if you are having more component into one of the streams, then it is better to separate that component rather than sending that component in all the downstream units. Okay, so remove the larger product stream first. For distillation, remove the product with the highest heat of vaporization first. If possible, this reduces the heating cooling duties of the subsequent units. Okay, so when you have any mixture of stream, when you can have different components in one stream, then it is better that you separate the product in the distillation process with the highest heat of vaporization first. Now what happens when you supply more heat, that the product will be separated at the first stage and will not be going into the subsequent units. If it is going into the subsequent unit, then you have to again supply high amount of heat. Okay, so at the first stage you supply heat, and from that stage you will get this product, and the other lighter or the low heat of vaporization products will be going to the downstream units. Do not recombine separated stream. So once you have the separation of the components, and do not recombine them. It's quite obvious. Do the easy separations first. Do the easy separations first. So whatever separation process is easy, it is more reliable to get those operations first. Do not waste raw materials and do not over purify the streams based on their uses. So depending on the product quality and the customer requirements, you have to purify the stream. If you over purify the stream, it will not have an economic benefit to the process. Remove hazardous or corrosive materials first. So if you're dealing with some kind of chemical that are hazardous or corrosive, then you have to treat them in the first stage, or you cannot just allow those material to go into all the processes or in all the downstream units. Okay, so you have to remove all the hazardous and the corrosive materials first from the process. Use the less expensive crude separation technique first, liquid-liquid extraction before chromatography. Now here comes the concept for the economics. Now chromatography, it is kind of expensive process. Liquid-liquid extraction, it is kind of less expensive process. So when you are going to select between different technologies, so it is better that you select some less expensive technique, and then you can move to the higher or the expensive techniques. Now, for the separation section, other important questions to be included. What are the product specification for all the products? Now, for any of the separator, it is very rare that you get 100% purity of any product, or or how you can, what should be the level of the purity or the impurities that are allowable in the product. So this demand comes from the customer side, and you have to match that demand. Product specifications are developed to satisfy customer who will use these products in their own processes. Okay, so it depends on the customer need. The most common specification is a minimum concentration of the main constituent, such as 95%. So this is not very fixed rule here, but usually the product quality, it should contain 95% of the main constituents. Maximum purity levels for specific contaminants may also be specified. So if there is some process which can be affected by a small amount of impurity, then the customer has to specify that one, and you have to meet that requirement, as well as requirements for the specific physical properties such as color, order, specific gravity. So these are some of the other requirements that can be asked by the customer, and you have to control the color, order, or the specific gravity also. A single separation technique may not be sufficient to meet all the required product specification. So when you are provided with certain kind of information from the customer, then maybe one separation operation is not enough to get all the required demands. Then you maybe need to switch to other separation techniques also to enhance the quality of the product or to meet the desired requirement from the customer side. In the production of benzene via the HTA of toluene, it is necessary to produce a benzene product stream that contains 99.5% benzene that is water white in color. Now there are two specifications. One is the purity level and other one is in the color. Okay, so it should be absolutely clear. If the feed toluene to the process contain a small amount of color, determine a preliminary separation scheme to produce the desired benzene product. Now, if there is some kind of color in the toluene, then how you can actually remove that color from the process, because the customer has demanded the absolute clear benzene product with this purity. Now, for this kind of operation, what you can actually do, you have to use some other kind of equipment to match the other requirement of the customer. Now, what we can actually do here, as a guide, look at the figure 1.5. So you can go and watch this figure 1.5 of the HTA of the toluene. Separation can be accomplished using distillation due to wide difference in volatility between toluene and benzene. So the first thing is very clear that benzene and toluene, they differ in their boiling point. So distillation can be a viable process to get the desired product. The second one, compound causing coloration is soluble in both benzene and toluene. Now, this is a limitation here, that there is some compound that can cause a coloration in benzene and toluene. So, how we can actually remove that one, and at which stage we have to remove that one? Okay. So, laboratory test shows that benzene can be decolorized by passing it through a bed of activated carbon. Now, this is one of the way that we can adopt to decolorize the benzene, that passing it through the bed of activated carbon. So we can pass the benzene through the bed of activated carbon to make it colorless like a clear water, thus adding an activated carbon adsorber as a second separation step to decolorize the benzene product. Now here we can add the activated carbon adsorber into the process as a secondary separation technique to meet the product quality requirements. Okay. Are any of the products heat sensitive? So sometimes if you are working in some food industry, then there are many products that are heat sensitive. So how you can manage those products without reaching that heat, and you can also, you should have to match that product quality also, or the product purity level also. So if you simply use a distillation column, then maybe that product would be deteriorate at that high temperature. Now what we can actually do? If any of the product or byproducts are heat sensitive, that is, they decompose or polymerize at elevated temperatures, the conditions used in the separation section may have to be adjusted. Okay, so what we can do here, so to avoid reaching that temperature to that can affect the product, we have to change the process conditions, especially the temperature conditions within the distillation column. So at one side we want to increase the purity by using the distillation process, and on the other side we cannot increase the temperature. So what is a viable way to achieve both of these things? So from the thermodynamics we know that we can reduce, or we can reduce the pressure, and thus we can lower the boiling point of the liquid. So we can adopt the similar technique in such kind of processes. So let us see an example here. It is known that acrylic acid starts to polymerize at 90 degrees C. Acrylic acid must be separated from acetic acid to produce the required purity product, and the volatilities of both acids are significantly different. This point to distillation as a separation method. Now we are having acetic acid and we can have the acrylic acid into the process, and the boiling points of these two components are very like there's a difference of boiling point is high, so we can actually use the distillation technique for the separation. Now what is the hurdle here? That acrylic acid, it can polymerize at 90 degrees C, so this is a limitation in this process. This points to distillation as a separation method. The normal boiling point of acrylic acid and acetic acids are 140 degrees C and 118 degrees C respectively. Now you can see that the normal boiling point of this acrylic acid is 140 degrees C, but it can polymerize at 90 degrees C. So how you can do the separation using the distillation column? How would the separation be accomplished to avoid degradation of the acrylic acid product? Now how you can do this thing? The distillation column The distillation column must be run under vacuum to avoid the problem of acrylic acid degradation. So if we can create the vacuum within the distillation column, then we can lower the boiling point of the acrylic acid. So below 90 degrees C, we can actually have the good separation. The pressure should be set so that the bottom temperature of the column is below 90 degrees C. So we can operate the boiling point below the temperature of 90 degrees C by reducing the pressure within the column. From figure B 9.1 and table B 9.1, we see that the column pressure of 0.16 bar at the bottom can accomplish the desired separation without exceeding 90 degrees C. So you can see these figures and the tables for the acrylic acid and the acetic acid separation process, and there you will see that the pressure in the acrylic acid separation column, it is below this 1.16 bar. So at this pressure you can have you can lower the boiling point of the acrylic acid below 90 degrees C. So you can have a separation using the distillation column, but remained at the temperature below the 90 degrees C and avoid the degradation of the acrylic acid. Are any of the products, byproducts, or impurities hazardous? So you have to see this question also, because separation between components is never perfect. Small quantities of toxic or hazardous components may be present in the product, fuel, or waste streams. Additional purification or subsequent processing of these streams may be required depending on their use on their end use. Okay, so you have to be careful about the impurities that can be in the product, byproduct, or in the waste stream, because it can be toxic and they can damage the environment, and also they can affect the operators that are working on the plant. Okay, so maybe if you are having some kinds of toxic or hazardous impurities in the process streams, then you have to carry out the special separation process to get rid of those impurities. Now let us see that how many distillation columns we can have for the separation of different components into the process. Now let us see a minimum of n minus 1 separators are needed to separate n components. Okay, so if you are having like 5 components in your feed stream and you want to separate all the 5 components, then how many number of separators of the columns you require? So the formula is n minus 1 separators are needed. Okay, so n here represent you the number of components, and this equation show you the number of separators that you require here. For example, here A, B, C are the 3 components, so you can use this formula. So 3 minus 1, you would be getting 2 here. So 2 columns would be required to separate these 3 components. So from here you can see A is coming from this first column and B and C is coming from the second column. Now choice of sequence depends upon economics. Now here you have to see that which columns that you have to choose and what should be the operating conditions of each of these columns. Okay, now for example, if you are using this first sequence here, now here and here it is the feedstock is same, but just the positioning of the towers are different. Now this positioning actually depends on the utilities that are being utilized and the cost of the raw materials and the recyclation that you need to have into the process. On this one, what you can see here, if the component C it is the higher boiling point liquid, then the heuristic says that we should separate the component C at the first column, and we have to separate the lower boiling liquids into the second column. So in that case, this design looks more feasible from the economic point of view and from the utilities point of view. If heavy component C is water, high heat of vaporization. Okay, now if we are using this kind of process, now the C here, it would be affecting this column also, and it will be affecting this column also. Okay, now here you are supplying heat. If there is C is a water, you are supplying heat here, and then you have to supply heat here again. Now the utilities cost will be increased. And now if you are using this process scheme, now here you are supplying the heat to separate the C, and then you can have the easy separation of A and B. So in that particular case, less amount of utilities would be required into the process. Now when you can use this kind of procedure or this kind of sequence, if heavy component C, for example, is having the higher heat of vaporization, if C represent the larger amount, so if the amount of the flow rate of C component is high, then you can use this kind of sequencing. And if C is only corrosive, and if C component is corrosive, then you can also have such kind of arrangement. Now let us see these columns in terms of lower utility cost and how many actually sequence we can make from the same process. Now from the formula, what we see here, there are three components into the process, and how many number of distillation columns we have to choose. For example, here we are having three components and we use the formula, so it tells us that we have to use two components. Now here for the same process, how we can actually reduce the utilities cost by increasing the number of equipment. So we have to see that what is the economic break point, and at which point should we operate the process. Now let's see this one here. For example, you can have these three components A, B and C. You would separate this way. In the top, on the overhead, you are getting A and B, and in the bottoms you get B and C. And then you can have two columns from here. You will get B, A, and you can have B here and B here, and then you can have C here. Now here you have increased the number of columns, so you have to see that, but how much utilities are being utilized for the separation of this one, and how it can be different from the separation that is occurring at this process. Okay, so you can have some idea from for the economics and the utilities that are being utilized, and then you can actually decide which column is more efficient in terms of energy utilization. And also if you are having if you are provided with the three components, then this is a new technique you might have heard about, which is a divided wall column. Now using this techniques, you can have these three components. Okay, so from the single column you can have these three components, which is also working in an efficient way. Now so at the end, what we can actually see that that in all of these techniques, primary aim is to reduce the utilities cost, and if the utility cost is lower than the capital cost, then always the process will be the economical. Okay, so the utilities, it takes a lot of energy from the overall process, so you have to consider the utility as the most important factor while deciding the choice of the column that you are having, or the number of columns that you are going to have in the process. Okay, so for example, if you are having three columns but the utility cost of this process is lower than this one, then in the long run this kind of sequence would be more beneficial. Number of alternate simple sequencing. Okay, so last one, it was about only the number of columns that you want to have into the process, but this one, it is giving you an idea that how many number of sequence you can have, how many different kind of designs you can make. Okay, so the number of different sequences that you can have for any process, it is 2 into n minus 1 factorial, n factorial n minus 1 factorial. So this is an equation that can be used to make an idea that how many different kinds of sequences we can have for the distillation column. Now let's see different kinds of processes in terms of separation and in terms of distillation column. Now for example, you are having some feed, and you can simply have some distillation process, and you can get some kind of distillate from the top, and you can have some bottom product. So this represents you the simple distillation process. But sometimes you are provided with a feed. What kind of feed? If it is having more like light components and less heavy components, so you can have this kind of system, which is called as a reboiled absorber. In this section, what actually happens here, it is used when light components are very dilute and do not need purification. Okay, so you put the feed and light components would be going here, and bottoms would be coming here. So this represents you this one stripping section of the column. Okay, so you can have just the feed stage near the top of the column. On the other hand, you can have the rectifying section, so it represents the section above the feed plate. Now you can see the feed is entering from the bottom, and you can have some distillate at the top, and here you can have the bottom. Now in this case, if you calculate the feed stage, it will be coming at the bottom by using the encapsulate diagram. Okay, so it depends on the type of feed. And It depends on the type of feed that you are dealing with and the number of components, either they are high boiling or the low boiling liquids, and what kind of distillation process is suitable for the for your study. Okay, so you can generate the appropriate feed locations for that particular column. Now let us talk lightly in terms of the azeotropic distillation. These are called as there could be two types of azeotropes. One is the minimum boiling azeotrope, which is also called as the positive azeotrope, and the other one is the maximum boiling azeotrope, which is called as the negative azeotrope. Okay, so I hope that you have studied these two kinds of azeotrope in your separation process course. But to just give you an idea, what is a positive azeotrope? Positive. These are the minimum boiling azeotropes, and these azeotropes, what they actually do, if you mix different components together, and the boiling point of those liquids decreases, then the actual boiling point of the liquid, then those represent the minimum boiling azeotropes. On the other hand, if you mix different components and the boiling point of the mixture increases as compared to the boiling point of the individual components at any specific ratio, then those represent you the maximum boiling azeotropes. Now, these kinds of azeotropes you can see in the chemical and the process industries. It is very common. So you have to see which kind of azeotropes you're dealing with due to repulsive forces between the molecules. So when the minimum boiling azeotrope happens, when there is repulsive forces between the molecule, azeotropes is at a lower temperature than higher than either pure component boiling. Okay, so when you make a mixture for this minimum boiling azeotrope, the boiling point of the mixture would be lower compared to the boiling point of the pure components. Now, once you have different kinds of azeotropes in the system, now which kind of different processes you can actually choose? Now, here in this diagram, B and F represent you the entrainer and A and C is binary azeotrope. Now, when you put this mixture into this feedstock, what actually happens? The B combines with the C and it will become higher boiling liquid and it will be separated at the column A. Whereas the F, it is combined with the component A and it will be moving forward. Okay, so in the next column you can have the separation between the A, and then you can have the recycle of the entrainer back into the process. Now, there could be another way of the binary azeotrope, that you can have simple distillation where the B, which is having the higher boiling liquid, it will be separated at the bottom, whereas the A, it will be going into the overhead stream, and then a secondary separation technique would be required if the purity needs to be increased. Now, the type C here, it represents your some kind of distillation process which is called as the heterogeneous azeotrope. Now, in this azeotropic mixture, what actually happens if the azeotrope is formed where two liquids are immiscible, then we have to use this one. Okay, so sometimes it happens that the azeotropic mixture, it is formed with the two immiscible liquids. So one of the immiscible liquid will be going to one column and the other one it is going to the one column. So this is a kind of handling the azeotropic mixture, having different immiscibilities into the process. Okay, then you can have different kind of azeotropes that differ in their properties when they are subjected to some kind of pressure. Now here, if we are increasing the pressure, what happens? If you are increasing the pressure, then the A will become the component with the higher boiling point, whereas at the lower pressure, the B is the component which is having the higher heat of vaporization. So you can use the separation technique for the azeotropes by increasing the pressure or reducing the pressure. Then similarly, when you have these kinds of sequences, then you can draw the feed location diagram by using the McCarthy diagram. Okay, so for A1, it represents you the simple distillation column here, so you can actually estimate what should be the value for the feed streams and what is the maximum point of the what is the maximum point at which you can have the separation, and for after this point you should have to use some other kind of separation technique. And now this one is the lower pressure and this one is the higher pressure. So this represent you this one the type D here. Okay, so you can see for the lower pressure you can have the different McCabe theory diagram, and for the higher pressure you can have the different McCabe theory diagram. Okay, so this is the sequence for the lower pressure liquid, and this one is the sequence for the higher boiling point liquid for the column. Similarly, if you are dealing with some kind of immiscible easy drops, then there are two columns here again. So what you can have for this one, for the low, for the first liquid in the column 1 having the immiscibility different than the column 2, you can have this kind of separation. Okay, so here you can see the feed location 1, and similarly you can have the idea about the feed location 2. Okay, now here you would see that the feed location 1 is here and the feed location 2 is here. Okay, so we can have the separation on the basis of the immiscibilities between the liquids. So this is all for today. So please let me know if you have any